All right, everybody, welcome back. We are going to go into some examples of projectile motion. Okay, so I have this first one. It states that a ball is thrown horizontally from the roof of a building that is 7.5 meters tall, and the ball lands at 9.5 meters from the base of the building. And we want to know what the ball's initial speed was. Okay, so we are going to kind of pick this apart. So the first thing I'm going to do is draw a diagram, okay, because diagrams are going to be very helpful when trying to understand the whole idea of the problems. Okay, so again, a ball here, we can say, is thrown horizontally from a roof building. Okay, so we can draw a building here. Okay, and it's thrown horizontally from the roof that is 7.5 meters tall. Okay, and it lands 9.5 meters away from that building. Okay, so we can assume that the projectile motion went as so. Okay, and we want to know the ball's initial speed. Okay, so I'm going to label a few things here. So my first thing is that I know that there is gravity involved. Okay, so I'm going to draw that out. Then I am going to say, let's see, the ball's initial speed. So that's going to be V naught. Okay. And my, let's see, the ball falls 7.5 meters in the negative y direction. Okay, so if I say that this is my y, this is my x, okay, this is going to be my negative y direction. So my delta y is negative 7.5 meters. Okay. My delta x is going to be 9.5 meters. Okay. And this is positive since we said that this is falling negative, this is going to be going positive. Okay. So there we have that. Let's see. And because it says that it was thrown horizontally, I'm going to say that there was no initial angle to this ball. Okay, so I'm going to say that theta naught is 0 degrees. Okay. All right. So I'm going to go back to my PowerPoint and look at these equations of motion. Okay, so let me erase all the pen here so I can just look at these. Discard, and I'm gonna go like this. Okay, so I want to know my velocity, my initial velocity. Okay, so I'm gonna go down the line, oops, and see which one has an initial velocity. Okay, in the x direction. Okay, so I'm gonna say, well, here I can see that my v initial in the x direction and my final in the x direction is constant. So this is gonna be the same as v naught x equals vx. Okay. Let's see here. What else do we have? So we can use this first equation, okay, to solve for our time. Okay, so let's see. We have x equals x naught plus Vxt. Okay, so this is also x minus x naught equals Vxt. Okay, and x minus x naught is just delta x, xt. Okay, so we know this, but we don't know either of those. Okay, so that's at least a starting point. Okay, so let's see what else we have. Our Vx and we can relate our Vx here to our V naught through, where is it? Let's see if I can find it here. Nope. Bear with me for just a second. Well, I guess I can just state it. Okay, I'll just state it. Our Vx, okay, can relate here by saying it's V naught cosine theta naught. Okay, so this is going to be our V sub x, V naught x, or our Vx. Okay, and then again times t. So this is going to be one of these equations. Now I can plug in my theta naught already. Okay, if I plug in my theta naught here as 0 degrees, okay, I'm going to get delta x equals V naught times cosine of 0 degrees. Cosine of 0 degrees is 1. Okay, so V naught times t. Okay, so this is going to be my first little equation here that I want to try to use. Okay, so let's see what other equations I have here. All right, so I can give you guys a minute to kind of think about which equation I will use. Let's see. I have my delta y, so that would be something like this, or like this, or like that. So that kind of narrows it down to 3 equations. I know what g is. Oh, I know what v naught is in the y direction. That's 0, right? Because my v naught y is going to be my v naught sine theta naught. Okay, and sine of my theta naught is sine of 0 degrees, which is 0. Okay, so this then is going to be equal to 0. Whoops. Okay, so why don't I use this equation? Okay, so this y equals y naught plus v naught yt minus 1/2 gt squared. Okay, so y equals y naught plus v naught yt, okay, minus 1/2 gt squared. Okay, so again, this is 0, so I can cross that out immediately. Okay, so now I have y minus y naught equals 1/2 or negative 1/2 gt squared. Okay, so that is really just delta y equals minus 1/2 gt squared. Okay, now what do these equations have in common? That time, right? So if I solve for time here, I can plug it into that first equation and solve for my velocity. Okay, so that's what I'm going to do. I am going to solve for t here. So I'm going to move some stuff over. I'm going to have a negative 2 delta y divided by g equals t squared. Okay, so I get negative 2 times my delta y, which was negative 7.5 meters, negative 7.5 meters, okay, divided by 9.80 meters per second squared, okay, equals t squared. And we want to take the square root of that because we just want time, okay? And luckily, we have a negative times a negative, which is a positive, okay? And we don't want a negative under there because that would give us an imaginary number, which is no good to us, okay? And remember, with the square root, it'll give you either a positive or a negative value. Of course, with time, there is no negative time. So we'll just have a positive value there. Okay, so let's see, 2 times 7.5 divided by 9.8, then take the square root of that number. Okay, so I get positive 1.24 seconds. Okay, so now that's the amount of time it takes for that ball to fall all the way over to here, to this final position. Okay, so I'm going to plug this number back into here. Okay. All right, so I'm going to do some quick algebra. V naught now is delta x over t. Okay, and my delta x is 9.5 meters. And divide that by my time, which is 1.24 seconds. Sorry, my nose keeps itching. All right, so 9.5 divided by 1.24 is going to be 7. Let's see, I can round that right there, 7.7 meters per second. Okay, so now I just solved for my initial velocity that ball was kicked. Okay? All right, so I know that was a little bit much, so I am going to do the next example in another video. Okay? All right.